Hello everyone, I'm Idris Ahmed Jae from Department of Civil Engineering, University Technology Petronas. I will be presenting my paper, Numerical Validation of Hydrodynamic Responses and Mooring Top Tension of a Turret Mode FPSO using simulation and experimental results. First, I would like to take us through the flow of the presentation. It will be in the following sequence. Introduction, description of the model and mooring system, numerical simulation, FPSO hull modeling, numerical validation, then results and discussion. First, for the benefit of those that are not from offshore background, I would like to start with the question, what is FPSO? FPSO is actually an acronym of floating production storage and offloading. It is a floating production platform used for in the oil and gas, especially in the deep sea. At the moment, it is one of the most used because of its numerous advantages, including large topside working area, stable hull, and large storage. When in operation, the FPSOs are held in position using mooring system. The most popular type of the mooring system, we have the spread and the turret. The turret is further classified into two, the internal and external. But in this study, we consider the internal turret, which is located at some distance along the length of the hull. And here we can see these are the mooring lines, which the study is mainly on, and the risers. These risers convey crude oil from the seabed into the FPSO, and these mooring lines try keep the FPSO in position, making sure that it is not, it has not um, gone a distance that will overstress the risers. So one of the most popular method or most reliable method for assessing the hydrodynamics of this FPSO when you is the model testing. However, the model testing also, despite its reliability, also have its own shortcomings. Due to the limitation of wave tanks, it is possible. It is sometimes very difficult to adequately proportion the mooring lines based on the um, based on the water depth in question. So in such cases, equivalent truncated mooring lines are used. However, due to apart from the model testing, another reliable method is to use validated models. Validated models in the sense that the the FPSO or any structure is designed numerically and validated against experimental results, which is what we did in this study. All right, so this is the FPSO we are considering or we consider in this study. It has length between the perpendiculars as 310 meters, draft of 15.12, length 315, and then it has a storage capacity of 1.4 million. And the mooring system, it has a internal turret mooring system, which is located at 8.75 from the forward perpendicular. That is from the top here. From this forward, it is 38.75 meters. Also, the mooring system consists of 12 mooring lines configured into 4 groups, each group consisting of 3 mooring lines. So we have group 1 to 4. And for each of these lines consists of 3 segments, the top, midsection, and the top. And and the bottom. The top and bottom are made of chain, while the midsection is polyester, as we can see in the figure with their properties. And also the FPSO is also acted upon by combination of environmental loadings, the current at 210 degrees, wave at 180 degrees, then wind at 150. So here, the numerical simulation, the processes involved. We use ANSYS Aqua software, and basis for the comparison, we use experimental results and the WIMPO simulation result from reference 1. And the flow of the numerical simulation is also, so first we model the FPSO using, we model the FPSO, then we define the line configuration, then diffraction analysis was conducted, from which we determine the hydrostatic forces, including diffraction forces, added mass and damping, then stability analysis, then hydrodynamic response component of the software. From there, using calm water, we conduct static analysis to determine the force exposure relationship, and using time domain analysis, we determine free decay time series. By calm water, we mean we deactivated the wave, wind, and current. Then, using the same component, but with the wave, wind, and current, we conduct time domain analysis to determine the 6 degrees of freedom and the mooring tension. So for the mooring, for the FPSO hull modeling, in the reference paper we have considered this midsection of the FPSO is given, which was imported into Maxoff, and then model, then exported to design modeler for modification, and then to ANSYS Aqua for meshing and further analysis. For the numerical simulation, we conducted 3 tests, which include the static offset test, the free decay test, and the time domain analysis test. The static offset test is majorly conducted to determine the restoring force of the mooring line, because that gives the idea of the ability of the mooring system to resist excursion of the FPSO under environmental loading. Then the free decay test was conducted to determine the natural period and corresponding damping ratio of the FPSO. Then time domain analysis was conducted to determine the 6 degrees of freedom of the FPSO and the corresponding line tension. So the aim of the validation is to try and achieve as close as possible the published results. So results and discussion. Here we have the comparison between the result we obtained from the Aqua model and the wind post. From this plot, we can see that there is a very close agreement between the published and the model we are presenting. So the maximum difference between these two results is 3%, which is very commendable. And then for the free decay test, we have compared the results in 4 degrees of freedom, that is for surge, heave, roll, and pitch. So here, from this plot, you can also see the agreement is quite very good. And from those plots, we try to determine the periods and damping ratio. where this red are the ones computed for aqua. So from this, if you compare by comparing this with the simulation, which is aqua, and the OTRC experiment, you can see that the results are also very close. In such, you can see the heave, roll, and pitch, and also the damping ratios are also very close. Then for the degrees of the hydrodynamic responses in 6 degrees of freedom, the here the original results are obtained in time domain, but for easier comparison, we converted it to spectrum using fast Fourier transform. From these plots, you can see that for such sway in this low frequency dominated, while and for heave and roll also for heave and roll they are wave frequency dominated, while for pitch and yaw you can see the pitch is wave frequency dominated while the yaw is low frequency dominated. And also the results you can see is well comparable with the published results. And so for the mooring tension, here we have the results for each of the group of the mooring lines. Here for group 1 and 2, you can see the result is also wave frequency dominated, and while 3 and 4 are low frequency dominated, but overall the results compared very well with the published result, although in group 2 this the Wimpus results is way higher than the two results, which according to the the comment in the paper, this is because of some or this is due to the lack of consideration of viscous whole viscous in the simulation. So based on the statistical comparison, also you can see the mean result also compared well with the experimental results in this group, and in this group also very well, and so also in the other groups. As a conclusion, the simulation result is appreciably comparable with the published results. Then the outcome model can be used as a benchmark for further parametric study on the hydrodynamic responses of FPSO mooring tension and restoring behavior of a turret mode FPSO in deep water. Then the whole viscous effect has proven to significantly affect the roll responses for numerical simulation. Thus, it is to be included for better responses. Simulation results indicated that FPSO responses in the horizontal plane, that is the surge, sway, and yaw, are low frequency dominated, while heave, roll, and pitch are wave frequency dominated. Based on the comparison of aqua results with 12 moorings, the established results with 4 equivalent mooring lines, the use of truncated moorings for deep water analysis can be justified. Then the low frequency component of the mooring tension spectrum appears significantly higher than the wave, thereby indicating that mooring tension is significantly influenced by slowly varying surge and sway motions. Okay, finally, the authors would like to acknowledge University Technology Petronas Malaysia for supporting this research under the YUTP grant with the number 015 LCO 116. Thank you very much.